Hello, everybody. I'm going to be talking about the development of sequential colimits in homotopy type theory. And since you're watching this talk, I'm going to assume that you already know everything about homotopy type theory. So we're going to be doing some cool mathematics in type theory today. And of course, the interesting mathematics will be the sequential colimits, also known as direct limits in the literature, which are colimits of a diagram of a particular shape that we can see here at the bottom of the slide. It's a very simple diagram, but yet sequential colimits are very useful for the semantics of programming languages, for example, as we will see shortly. So I'm just gonna very briefly go over some basic concepts from homotopy type theory that we're gonna need for today's talk. So we all know, of course, by now that types are spaces and terms are points, and proofs of equality can be seen as paths from X to Y. The only higher inductive type we shall need is the sequential colimit itself. And we will not be making explicit use of the univalence axiom, although of course it is absolutely necessary for the development itself. So here are some pretty pictures from Dan Licata that show why types can be thought of as spaces and why the equalities from M to N can be thought of as paths from M to N, and why, for example, Q is not equal to M. And we have the standard operations on paths, inverses, identities, path composition. And of course, here's a picture showing why not every path is equal to every other path. And so here are some actual notions that we will be needing for our technical development later on. So of course, every function from A to B has a functorial action on paths, and a type family B over A is a function from A into the universe, so it also has an associated functorial action. And this means that it carries a path P from X to Y to a path in the universe, which is an equivalence between Bx and By. And the equivalence is almost always the one you expect. So for example, if we have a fixed point A and we define the type family to map Z to the type of proofs from A to Z, then the induced equivalence is just the obvious one, post-composition by P. We're also going to need to know when two pairs, points in sigma type, are equal. And this is also the obvious thing. A lot of homotopy type theory is completely obvious in retrospect. So two pairs are equal if their first components can be related by a path P, and the second components are related by the induced equivalence. So we're also gonna need to know when a type is contractible, and this is when it has a particularly trivial structure where any 2 points are equal. And one instance of a contractible type is the so-called singleton type, which consists of, for a fixed point A, consists of all the points in A that are equal to A together with their proofs. And using the information on this slide, it is enough to show, it is in fact very easy to show that any singleton type is contractible. So this is pretty much all the homotopy type theory we will need to carry out our technical development. So in this sense, our treatment of sequential colimits is completely elementary. Let's look at why a computer scientist should care about something mathematical like a sequential colimit. And that's because many constructions in the semantics of programming languages in fact take the form of sequential colimits. For example, there's a standard fixed point theorem, I think originally due to Adamek, that says that if we have a category with an initial object and colimits, and then we have an endofunctor that preserves sequential colimits, then it has initial algebras, and such an initial algebra can be explicitly constructed as a sequential colimit. Sequential colimits also occur all over domain theory. For example, Scott's D-infinity model of the untyped lambda calculus can be defined both as a limit of projections and as a colimit of embeddings, as a sequential colimit as embeddings. So we can reason about D-infinity by using two different universal principles, which is very convenient. So this was something about sequential colimits in mathematics, and now how about sequential colimits in homotopy type theory? Well, the sequential colimit of such a diagram is constructed by first taking the disjoint union of all the A's, and then we identify each A belonging to AN with its image under Fn that lies now in AN plus 1. So we capture this in homotopy type theory as a higher inductive type with a constructor that injects iota n that injects from AN into A infinity. So that's the injection part. And then we have the gluing part. Glue n identifies the injection of A from AN with the injection of FNA from AN plus 1. So as the name suggests, there is an associated induction principle, and we're going to be here on the slide, we explain the easier version of the induction principle, the recursion principle, which says that if we have a type and an associated family of injections into this type and a similar family of gluings, so E is endowed with enough structure to itself look like a sequential colimit, also known as a cocone, then we have a unique function. We have a function from the colimit into E that preserves the constructors in a suitable way, and this function is in fact unique in the precise sense that if we look at all the structures that combine the function together with the proofs that such a function correspondingly commutes with the constructors, then this type is going to be contractible. So in a sense, a sequential colimit is initial up to propositional equality, homotopy initial, in the category of algebras of suitable form. So the induction principle looks just like this, except it considers the case when E is not just a type, but it's a type family fiber over the colimit itself. So now we came to our main theorem, which says that sequential colimits appropriately commute sigma types. And one could ask, what is so special about sigma types, or why we care about the commutation of colimits with sigma types? And the answer is that categorically, sigma types correspond to a certain type of a limit. So we're actually talking about commuting limits with colimits. And this is, of course, unknown in the literature. There is a classical result in category theory that can be found, for example, in MacLane, which says that filtered colimits commute with finite limits. And then there is an infinitary version of that, which says that it can be found, for example, in Lurie's book, that colimits over any kappa filtered category commute with kappa small limits for a cardinal kappa. And we have a similar result for infinity one groupoids, infinity one categories. So all of this is well known, but if any of you have the book and look these theorems up, then you will find that they occur after a lot of development. So there's a lot of preliminary stuff that needs to be carried out before one is able to carry out categorical proofs of these theorems. And so the goal of synthetic homotopy theory is to avoid having to go through setting up these preliminaries, because we we want to be able to ideally code this up without having to code up all of mathematics. So back to homotopy type theory. So we are going to be looking at the setup where, in addition to having a diagram of the A's as we had before, we also have a diagram of B's where now for each n, we have a type family Bn fibered over An. So using borrowing the notation from categorical logic of fibrations, we can write this as in the diagram that's in the middle of the page, where we put Bn above An and think of it as a family fibered over An. And then for each A in An, we have a way of going from the fiber of Bn over A to the fiber of Bn plus 1 over Fna. And we can again draw this as a Gn lying over Fn. So given a setup like this, one obvious way to make sense of it is to combine each Bn with An into a sigma type and ask for a colimit of a diagram like this. We will see that on the next page, where we will have a colimit of sigma types. And another way that we can form a colimit out of all of these pieces is if we fix a point A in An, then we can form a diagram like this at the very bottom of the page, where we start with the fiber of Bn over A, and then we have, that's the first type or the 0th type in the chain, and then we have the fiber of Bn plus 1 over Fna, and so on. So what this really, then we can ask for a sequential colimit of this diagram. And in fact, this can be made into a type family over the colimit of the A's over A infinity. So not over any specific An, but over the whole colimit. And then we can ask how the total space of B infinity relates to the sequential colimit of the sigmas. And the answer is, of course, that they're equivalent. Otherwise, there would be no such talk here. And so why is this useful? Well, this is useful because the first type, the sigma of two colimits, is in a sense a very unpleasant type, because it contains two colimits that are in fact nested. So whenever we want to reason about it explicitly, we have to carry out a nested induction, and that is something we don't like and we want to avoid. Whereas the latter type, which is a sequential colimit of sigma types, is very easy and pleasant to work with. So we really want to, we really do want these two types to be equivalent. That makes our life a lot easier. And fortunately they are, and the proof of this fact doesn't actually rely on any categorical knowledge whatsoever or any knowledge of homotopy theory. All we do is we use the associated induction principles and some path algebra. And the gist of the proof is that we show that the total space, the sum of the two colimits, satisfies the induction principle of the colimit of the sums, and thereby they must be equivalent. And of course, since we have a proof in homotopy type theory, and Mike Schulman has recently shown that we have an interpretation of HOTT into infinity one tuples, this implies the corresponding result for infinity one tuples, which we already knew anyways by the previous slide. But this is a different proof. So, and the advantage of this proof is that it can be coded up. It is coded up in Lean and Calc and maybe in some other proof assistant already. And it's actually surprisingly short. It takes about 300 lines, assuming a decent library and a decent proof assistant. So not very much at all. And now we can look at what we can actually do with this theorem. So, I mean, the general answer is that this theorem can be proved to give very short, can be used to give very short proofs of a number of corollaries, which we will see later. And we will go over probably the most important one of them, which is characterizing the path space of sequential colimits. So unsurprisingly, the path space of a sequential colimit is the sequential colimit of path spaces. And so why is that? Well, so intuitively, any path from A to B in A0 can be injected into a path in the colimit between the injection of A and the injection of B. But likewise, we can do the same thing for paths from F0 of A to F0 of B, now in A1, and inject those. And since we know that the injection of A from A0 coincides with the injection of F0A from A1, this in fact again gives us a path between the two desired endpoints. But there is some gluing necessary, because if we start with the path B from A to B in A0, and then we carried along F0 into A1, and then we injected into the colimit from A1, this doesn't gain anything interesting, because we could have just as well injected the path P itself directly from A0. So some gluing is necessary there. And how do we prove this? Well, of course, I gave the punchline away already. We prove this by using the main result. And so probably the most creative part here is defining the actual family of type families B. And how do we proceed? Well, given X that lives in AN, we somehow want to compare it with the A down here that lives in A0. And how do we do that? Well, first of all, we need to make sure that they live in the same type. So we lift the A, we carry the A through along the chain of these Fs that we have, F0 up to Fn minus 1, to make sure that we end up with something that lives in AN, and then we can compare that with X. We can form the type. And so the proof proceeds in two steps. So first we invoke the so-called encode-decode lemma, which I believe it's a technique that's originally due to Dan Licata, and it's very easy to prove. We show that assuming that the total space of B infinity is contractible, then the type that we want to characterize, the type of paths from the injection of A to the injection of B, is in fact equivalent to the fiber of B infinity over the injection of B. And since we very cleverly defined B in a way that makes this exactly what we want, so the fiber of B infinity over the injection of B is going to be precisely the colimit of a diagram like this that we had in the theorem. So we're done assuming that we can carry out the second step, which is showing that the total space of B infinity is contractible. And of course, the total space means here a sigma type of colimits. So a sigma type of colimits is equivalent, as we know by the main theorem, to the colimit of sigma types. So it suffices to show that this colimit of sigma types is contractible. And how do we do that? Well, again, by our very clever definition of B, each of these types that occur in the diagram up there is a singleton type, which means that it's contractible by our observation from slide number 4, maybe. And then we're down to showing that the sequential colimit of contractible types is contractible, which is, again, fortunately true and very easy to prove. So we're done. So in a sense, this main theorem allows us to carry out very short and elegant proofs of many results like this. For example, we have similar commutation results with homotopy fibers, loop spaces, truncations, and we also can very easily show that homotopy, that sequential colimits and homotopy type theory preserve the truncatedness and connectedness and all these homotopical features. So now the question is what to do next with this development. Well, one can do, of course, much more synthetic homotopy type theory. For example, we can do localizations. I think Dan Christensen had some development that relied quite heavily on this result. Or we can go the more computer sciencey route and explore connections with the semantics of programming languages. For example, would it be possible to construct Scott's D-infinity inside HOTT, and what would it actually tell us about the corresponding result in infinity one groupoids? So if anybody wants to collaborate on this topic, I'll be more than happy to. So shoot me an email. Thank you very much.